Welcome, folks. Welcome to SAMPE's Tech Briefing webinar. Really pleased that you have joined us. My name is Raj Manchanda. I'm the Chief Technology Officer of SAMPE. Along with me is Miss Alexandra Principe, and also our moderator is Dr. Bob Yancey of Hexcel. We have a great webinar for you today. You're going to get to learn a little more about SAMPE technical committees and also some emerging trends. So Alex, did you have a message for the folks, please?
Welcome. If you can please introduce yourself, enter your name, title, job position, and geographic location in the chat.
Great, thank you, Alex. That's a great way for us to get to know each other virtually. So again, as Alex mentioned, in the chat, please enter your name, your title, your company, and your geographic location. We expect a large turnout today, so looking forward to hearing from everyone. Thank you. We'll start at the top of the hour, so we have a few minutes before we start. For those who've joined early, thank you so much. My name is Raj Manchanda. I'm on SAMPE staff, joined by Miss Alex Principe, also on staff, and moderating today will be Dr. Bob Yancey. The presenters from each of our technical committees include David Leach, Felix Chen, Jia Huang, Chris Smith, Bill Viviano. So we really are excited about the webinar today and look forward to presenting some new information to you and having you learn more about SAMPE and our technical committees and our upcoming Long Beach conference. Folks, as you join in the webinar, please enter in the chat your name, your title, your company, and your geographic location. We will start at the top of the hour. So thank you folks who are joining early. Thank you for joining, colleagues. You're at the SAMPE Tech Briefing webinar. We welcome you. My name is Raj Manchanda. I'm on SAMPE staff, accompanied by Ms. Alex Principe and several of our technical experts from our tech committees. Please go ahead and in the chat, enter in your name, your title, your job position, your company, and your geographic location. We can get a chance to introduce ourselves before we start at the first of the hour. This webinar will be recorded, and we also will welcome questions in the Q&A function. So please think about any questions you have. They will be answered towards the end, but they will be in the Q&A function. Welcome, colleagues. We look forward to sharing SAMPE's expertise with you. We have a great lineup of speakers today. We have David Leach from ATC Manufacturing, representing Thermoplastics Tech Committee. We have Dr. Felix Chen of Chimeta Corporation, representing bonding and joining. We have Dr. Jia Huang of the University of Southern Mississippi, representing the Sustainability Technical Committee. Dr. Christopher Smith of ACCI Specialty Materials, representing the Materials at Extreme Environments Committee. And Phil Viviano from Whisk Aerospace, representing the Advanced Manufacturing Committee. We welcome you to today's SAMPE Tech Briefing and look forward to sharing emerging trends with you and also what our committees are doing. We look forward to seeing many of you join SAMPE after this webinar and join our technical committees. Please go ahead and in the chat, enter in your name, your title, your company name, and your geographic location. Thank you for joining, folks. We look forward to a good turnout today for SAMPE's Tech Briefing. We welcome our panelists from each of our technical committees, and we also welcome our moderator, Dr. Bob Yancey of Hexcel. Today's presentation will feature updates from each of the technical committees and also some notions on emerging trends in each of the spaces that they cover. We look forward to inviting you to our SAMPE Long Beach event happening next month, May 20th to 23rd, and also our future CAMEX event. For those of you who are new to SAMPE, please go ahead and in the chat, enter in your name, your title, your company name, and your geographic location. We will start very soon at 1 p.m. Eastern in a few minutes. Welcome, colleagues. Thank you for joining SAMPE's Tech Briefing. We look forward to sharing updates from each of the technical committees today. We also have information on upcoming SAMPE events and SAMPE's products and services, including our State of the Technology Industry Report that is available on our store. We look forward to welcoming you. Please go ahead and in the chat, enter in your name, your title, your company name, and your geographic location. We expect a large turnout, so very grateful that you've joined the SAMPE Tech Briefing. Dr. Bob Yancey, I'm going to call you to the stage as moderator for this webinar. So we'll have Bob Yancey start to go live and introduce our first speaker. Again, as you join our webinar, please go ahead and enter in your name, your title, your position, and your company and your geographic location in the chat. Questions and answers can be entered into the Q&A function. And towards the end, we will address questions and answers, and we look forward to seeing you at our upcoming SAMPE Long Beach event. Bob Yancey, welcome you to the screen.
Okay.
Great, thank you.
Well, welcome everybody. We still have some people joining, so look forward to the participation today. This is really a report out of the excellent work that our technical committees have done over the last couple of years. They published the first ever SAMPE State of the Industry report. And this webinar is really to provide updates and talk about especially the emerging trends that are coming in each one of these technical areas. This is for information for those that attend, but from all of you, we would encourage your participation if you're not already actively involved in a technical community, technical committee. And there'll be more information at the end of this webinar in terms of how to join a technical committee if there's any of these that appeal to you. So with that, in regards to Q&A, each presenter is going to present about 10 minutes worth of material. If you have questions, please enter them in the Q&A. We're going to hold all the questions until the end of all the presentations, and hopefully we'll have about 10 minutes for Q&A at the end. So just enter those questions in the Q&A panel as we go throughout the presentation. So with that, I think we're ready to start on that. And so our first presentation is going to be by David Leach from ATC Manufacturing, who currently leads our Thermoplastics Technical Committee. So David?
Yeah, well, thanks, Bob. Yeah, so this presentation from the Thermoplastics group is jointly from myself and Julieta Barreto-Robles. We are co-chairs of the Thermoplastic Technical Committee. Julieta is at the National Research Council of Canada. And we also want to acknowledge Cedric Dupart from DAER, who provided some of the information for these slides. Cedric is also a member of the Thermoplastic Technical Committee. So we wanted to talk about an area that is very relevant and important in thermoplastics for us right now, and that's the ability to use welding for the assembly of thermoplastic composite parts. We have multiple potential techniques of joining parts together, including mechanical fastening, adhesive bonding, and welding. And obviously, compared to other composites, welding is a unique opportunity because of the ability to remelt thermoplastics. There are certainly quite a number of benefits in terms of cost reduction of the joining process, saving weight, particularly through elimination of fasteners, mechanical type fasteners. The fact that welding can be a very short cycle time, so it can really reduce the time for assembly and giving improved performance of the joints. But we have to acknowledge there are some challenges. It is a welding process, and so verification of the process conditions in that weld area are very important to ensure that we consistently achieve the expected performance. Getting access to the joint, whether you can get to it from both sides or maybe only from one side. Obviously, for the melting and joining process to go on, the parts being joined have to be in intimate contact. And that can also be related to the pressure application at the joint to ensure we're getting good contact. The temperature control, particularly in the immediate weld area, but of course you also get a heat affected zone in the materials adjacent to that. That might only be a small area, or it might affect a much larger extent of the part, right through the thickness of the parts being joined. Many of the thermoplastic polymers we use are semi-crystalline materials, and therefore the cooling rate at the joint and achieving the right level of crystallinity. And then, of course, the actual certification process that we're going through as well. But certainly welded assembly and also using these processes for joining are quite a big opportunity in the thermoplastic area right now. Now, we have quite a range of different potential techniques. Looking at this chart here, conduction, in other words, just direct heating of the two parts being joined. Obviously, you have to have pressure present there in order to ensure that they're not going to deconsolidate. Then there are a range of different induction welding. With carbon fiber, you can actually use the induction process to create electric current in the carbon fiber, and so use the carbon fiber itself as the medium to heat up during induction. You can use a susceptor, usually a metal mesh, in order to induce the current in the weld area. A kind of proprietary system called innovative solution welding, which uses a moving susceptor that goes under the coil, heats, enables the local area to be heated, but because that susceptor moves along, it moves out of the way, and so does not become incorporated into the finished joint. Koch and Van Engelen, owned by Daer in Europe, have their own proprietary induction system. Then there's various ultrasonic techniques, just a local kind of what you might consider a spot welding. But there's also quite a lot of work on moving dynamic ultrasound to join long joints together. Then there's resistance welding. Again, with carbon fiber, you can actually apply a current directly to the carbon fibers and allow them to heat up. Or you can put a metallic susceptor in and apply the resistive current that way as well. And then direct heating methods of the areas to be joined, such as laser or even infrared. So we certainly have many different techniques available. So let's look at the current kind of situation, because there is quite a lot of welded structure actually already flying around and has been for more than 20 years. Certainly GKN Fokker in Europe has been a leader in this area, with first of all the A340 and then the A380 JNOs with both resistance and induction methods. Also with resistance welding Airbus Atlantic, with the A320neo air intake acoustic panels. These are all flying parts that are being demonstrated on here in production. With induction welding, again, GKN Fokker in the Netherlands, the Gulfstream G650 control surfaces for the rudder and elevator use the induction process. And then also the Aviacomp in France with the A220 fuel access panels with a pan area and a stiffened structure being welded together with induction. And then Aviacomp also uses a conduction welding process in the A350 fuel access covers. So these are all established welding processes that, as I say, are in production, have been in service for many years successfully. But for the future, we see very high rates are going to be required for composite structures in aerospace. There's industry projections of something like a demand for 40,000 aircraft, commercial aircraft, over the next 30 years. And certainly the next generation of narrow body aircraft, we're talking about building at 80 or even higher per month. Advanced air mobility, air taxis, we see being built in very large quantities, thousands per year. And then there's a very wide range of autonomous vehicles, drones, and so on, of all sorts of different sizes and uses that are going to be built in very high volumes. So thermoplastic composite welding is really an enabler for the high rate assembly of these processes. Now, to support that, there are a number of development and demonstration programs that include welding, such as the Clean Sky program in Europe. In fact, the illustration over to the right is from the German Aerospace Institute, DLR, where they developed an automated moving ultrasonic stringer welding process, quite a complicated setup there, as you see, that moves down the length of the stringer to weld them to the skins. The NASA High Rate Composites Manufacturing Program in the USA, or HICAM program, is doing a lot of work on different technologies of welding. And then a program in Europe focused more on repair, called RETPAIR as well. And so these programs give us the opportunity to mature this technology to high TRL and MRL levels for high rate manufacturing. And to kind of wrap up on the next slide, I just want to mention we talked about the SAMPE Long Beach coming up in about a month's time. At SAMPE Long Beach, the Thermoplastic Committee is running a panel on welding and repair of thermoplastic structures. This promises to be a really interesting panel session, starting from kind of some of the basics and fundamentals. Eric Jankowski at Boise State University will talk about the molecular dynamic simulations of what happens when you bring two surfaces together and how the molecules will actually flow at the join, the fundamental properties involved in that. Michelle Van Toren, who is a technical fellow at Collins Aerospace, will talk about the welding process and the aspects of certification. Julieta will, from National Research Council of Canada, will talk on the repair aspects. And then Cindy Ashford from the FAA will talk about certification and particularly how thermoset bonding and thermoplastic kind of joining relate to one another. That session will be on the Wednesday afternoon at SAMPE Long Beach at 3:30. So we certainly hope that you'll be attending the conference and we'll have the opportunity to join us. So thank you. I have to say to the audience, unfortunately, because of some business commitments, I'm going to have to drop off. But if there are questions related to this, please make sure they go in the Q&A and I will answer them at a later date. Thanks.
Great. Thank you, David. And again, if you have questions for David, please enter in the Q&A. We'll make sure and get those to him. And also for all of you, if you've got questions ongoing that we're not able to address here, join a committee and you'll have a community to be able to ask those questions. So next up is Felix Chen, who's going to talk about updates on the bonding and joining committee. Felix?
Just waiting for, there we go. Okay. All right, this is me, the work of me and Hardik. I don't think he's here, but Hardik is the chair. I'm the vice chair. Next slide. Yeah, could you put it in presentation mode, maybe?
Oh, apologies. One second. Alex, in the meantime, you can run the first poll.
Okay, yeah. So even though this is short, I thought I'd put some content here just to put it in context. So I'm going to talk about some of the, what I see is some of the promising trends in adhesion. And then when there's adhesion, there's potential failure. So I want to talk about some of the trends I've seen that predicts and characterizes this failure. And I'll just touch on the State of the Technology report. Next slide. Also, there's a poll that's blocking part of my slides here.
Alex, maybe we'll turn that off. Yeah, sorry.
Okay, next slide. So on emerging trends, one here is part of a webinar that Professor Davud Asghari gave. I think I saw him on this chat, but this is straight from his work, and it deals with using composites and the actual fibers to improve adhesion. And the pictures on the right are plucked from his work. The top one there shows how the fibers are, how he's able to fabricate them to create the coiling that improves the adhesion. The chart at the bottom shows the increase to the strength. And one thing that struck me is that usually in materials, when you increase the plasticity, you decrease the strength because of the competition between flow and fracture. Here, this is not the case. He's able to get an increase in the toughness and an increase in the strength. Another thing I want to point out is that the adhesion here depends hugely on entanglement and intermingling. That kind of goes against the conventional wisdom that there's a lot of a role played by surface energy and chemical bonding. And if you've ever seen the work of Professor Kevin Kendall, he did a lot of this work in the 70s, but he has debunked a lot of the usual guidelines about increasing surface roughness and surface energy and focus more on the entanglement. And this work with Professor Asghari goes right in hand with that. And some of the presentations I've seen in previous conferences also supports this type of work. The next slide. This is from Dr. Yao Chow from the Pacific Northwest National Lab. He also gave a seminar on this, and I met him at the CAMEX meeting last November in Atlanta. This is some work he's done in improving adhesion using a plasma treatment. But the distinguishing feature here is he's using a fracture mechanics model, which is near and dear to me because part of my PhD work was in this. Now, the fracture mechanics, in case you're not familiar, there's a conventional one. And then in more recent decades, there's been a move toward a quasi-brittle, which incorporates a cohesive softening model. One of the features is there is a size effect that affects your results. What his work does here is to take out that size effect and show that the adhesion is independent of the geometry. And that's what he has done here, where he's showing that you can increase the strength and adhesion regardless of what delamination size you want. And that's what you need for a better treatment here. And this is an extension of the quasi-brittle fracture mechanics work that he has done and that in the literature has become more prevalent in the last couple of decades. But that's a newer extension of the classical fracture mechanics work coming out of George Irwin and Griffiths and that work. Next slide. So on to failure. Usually the mainstream classical failure theories are based on static stresses like von Mises, Tresca. They're just, you create a stress or you predict a stress using finite element modeling, and then you plug in, and if it equals some criterion, usually yield strength, then you're good. There have been some I've seen recently where the criteria are extended beyond that. One is the MAT, the multi-axial time temperature, and this improves upon the textbook failure theories. First, it's grounded in the actual physics. The most common, probably the most common failure criterion for metals is the von Mises. It's been tried to put on theoretical grounds, but it's an empirical based criterion. This incorporates not only the physics, but it also has damage evolution. So that is a dynamic evolution, which the importance, I'll talk about that in a second. But what it does is, what he's done, oh, sorry, can you go back, Raj? Okay, what it does is that it predicts polymer creep and ratcheting. And that ties into another presentation I saw last year by Yi Chen and Lloyd Smith of Washington State, where you take the viscoelasticity, the time dependence into the failure mechanisms, which normally they're not in there. And one thing out of this is some of the work I've done, this model, the second one, the Chen and Smith model, predicts the ratcheting, which I have seen, but which is not predicted in the classical failure model. So when I saw that talk, I thought I got to include that in this. I think it's a promising trend. It's more really suited for finite element modeling. And I talked to Yi afterward and asked her a couple questions, but I think these two models address some of the shortcomings in classical failure theories. And last slide. I'm going to incorporate some of these into the State of the Industry report. And I have a talk at the Long Beach meeting next month that touches on some of these. One thing I want to mention is for future trends for AI. I was at a conference last year, which was AI themed, and one of the trends was that a lot of the black box AI models are more static dependent, and they use Markov chains where the transitions are static. But these models here potentially can inform better AI models because they're dynamic, and they hence allow better prediction of one-off events rather than the current mainstream events that might happen. So I'm going to probably incorporate some of that also into the State of the Industry report, the AI. I'm not an AI person, but I went to this talk and I thought that is a great idea. I think these models can be put into that. So any questions you can put in the chat or I'll be around. Thanks.
Great, thank you, Felix. Alex, did we want to share results of the poll? Okay, so we've got about 70% SAMPE members, so that's great. For those that are not SAMPE members, you do not have to be a SAMPE member to join a technical committee, but we certainly encourage you to join SAMPE and get all of the other benefits of being actively involved in this advanced materials community. Okay, so for our next presentation, it's going to be on sustainability. This is a name change on this technical committee. It used to be recycling. We decided to really expand it to talk about not just kind of end of life, but also what we can do in other aspects of materials development and material processing that creates a more circular economy. And so Xie Xiong from University of Southern Mississippi is going to present the latest on the Sustainability Committee. So Xie.
All right, thank you so much. Yeah, hello everyone. My name is Zhe Qiang, and I'm Assistant Professor of Polymer Science and Engineering at the University of Southern Mississippi. I'm also the Vice Chair of the Sustainability Technical Committee, and join with Matt as well as Spencer, who from TCI and Northrop. So our tech committee really focuses on how to develop materials and a system that towards a more sustainable future, which is an emerging and very important topic for the future manufacturing in composite, but also many things beyond in a general materials world. So our committee look at this from 3 different angles that we're going to cover through. The first is end-of-life management. So if we think about the life cycle materials, and in order to build a closed loop circle, what really important here is think about end of life of these materials and reuse them. So there are 3 ways we can really look into. The first, of course, is reuse and repair. That includes that, not simply discarding materials, but rather repair them, or from a material design perspective, we could think about in a way that it build up like healing or self-healing capability in a material, so they can actually be fixed in situ or in real time in a way that these materials can have extended lifetime. But if they are considered as waste and have to be discarded, there are typically 2 ways to recycle these materials, including mechanical recycling as well as chemical recycling. Mechanical recycling is pretty straightforward. That is very common, usually for thermoplastic materials. In general, what you do is just grind them, shrine them down, and then reprocess them to a new material or new products through additional manufacturing steps. So during this mechanical recycling process, we do not alter the chemical identity in general. You may have some transition or chain crosslinking happens because of the high shear, high temperature environment. But in general, the chemistry itself is not changing. So you just really try to generate materials. But we also recognize that the challenge of mechanical recycling is that even though you have the same material chemistry, the material property can often be degraded, especially as a function of recycling events. Alternatively, for thermoset or crossing materials, a more common approach to address this is chemical recycling, which means that you do change the chemical structure of the materials. The common approach is including pyrolysis or catalytic degradation to recover these used plastics or used crossing materials to new chemicals or building blocks, and then build them back to the manufacturing process. So in this case, as you can see here, they may cause more energy consumption as well as cost. But in that case, some of the crossing materials have to go this circle because they are not very mechanically reprocessable here. So again, to recap the end-of-life management, first, of course, we need to think about it, reuse and repair that include developable self-healable materials. And then we can think about recycling, upcycling. That also includes efficient sorting, separation of the materials in carbon fiber composite. We need to separate carbon fiber from the composite matrix. mechanical reprocessing and chemical transformation represent two general routes to extend the lifetime of these materials. And also in the recycling process development, it's also important to think about life cycle in terms of their carbon footprint. And in general, we believe that the solution should not be more carbon emissive than the original material manufacturing process. But sustainability is not just about materials. Another very important thing here is we believe is low energy processing here. What does that mean here is basically if you think about the future manufacturing route, it is important to think about the use of low carbon energy resources that includes solar, wind, and hydrogen. And in that case, we may be able to generate electricity through these renewable energy resources that as well as the heat materials, and then leverage this renewable electricity or renewable heat source, and then we can build up into process design to inherently build a process where it's more energy saving compared to conventional processing. So in that regard, there's multiple factors we need to consider here. For example, like I said, the clean energy resource, the renewable energy resource is really important. And the solar, the wind, and the hydrogen have been identified as a clean energy. Also has been strongly pushed by Department of Energy by multiple grants and research opportunities here. We all know that, for example, solar cell is what you convert solar to electricity here, but also in addition to that, there's multiple ways to generate heat efficiently through the electricity input that includes things like electrical or resistive heating, plasma heating, or microwave, where you can reach the same temperature as conventional heating, but they are much more efficient due to the higher heat transfer or the mechanism difference from heating itself. And in addition to that, process design is really important. One thing that we recognize here is that additive manufacturing is really useful in that regard because they are inherently less wasteful compared to other methods, right? By building materials layer by layer, this does not involve subtractive method or like conventional processing, which will generate less waste in the process. But in addition to that, we also believe things like data management or data science and AI will be useful to directly predict, optimize process condition that will also involve less trial and error tests here. So these are the important factors we want to consider in low energy processing here. And next slide, please. And the third thing towards sustainability is really about the precursor materials, right? How we can actually build up things, because a lot of the chemicals we're using is fossil based. And then there's a lot of push towards the bio-based materials. Though we recognize that sometimes the bio-based material does not necessarily become more energy saving in terms of their production and compared to fossil-based stuff. But we also believe there's a lot of routes that we can really balance these two by exploring further about the bio-based system. So there are multiple things we can think about here. Of course, polylactic acid is one of the most commonly used bio-based polymers, but also there's a lot of excellent work talking about things like bioplast-derived composite materials, as well as protein-based material that has offered comparable mechanical properties, but the material itself is more sustainable and does not involve more energy-intensive mechanism to develop the building blocks. So these are very important things. We can consider the bio-derived precursor and building blocks, and the nature of these materials can facilitate the biodegradation as well as biocomposition here. Other opportunities we also explore here is that, and really inspired by several recent calls from Department of Energy, that carbon dioxide-based chemicals for advanced polymer composite would be a really interesting way to look at, because this also involves the CO2 utilization, which is an inherent part of the building cycle for the carbon negative emission here. So this would be an additional opportunity. So we could think about moving forward to leverage these materials as a part of the sustainable circle for the future economy here. So just to recap a little bit, the future is really about thinking about how to build a circular materials world. And there's three major aspects: robust and sustainable feedstock, building recyclability through advanced chemistry. That includes also something that is really popular now is like reprocessable polymer network. But also we want to build up features, allow efficient separation for composite in a way that we can separate, for example, fiber materials from matrix more efficiently here. From a process design perspective, the use of energy and renewable resources is very important. The heating that is energy efficient is also important, and also using advanced manufacturing such as additive manufacturing or AI-informed process design, we want to build up a system that is less waste generation during the process. And overall, we think what is really matters here is an integrated system level design to enable both economic and environmental benefits, because we believe these two have to be coupled to push the world forward for getting a more sustainable future. And that's all our results and report. Thanks so much.
Okay, thank you, Shay. On this, again, if you've got questions on sustainability, please enter those. And we've gotten some good questions so far, so thanks for those. There was a question already about will the recording of this webinar be available? And the answer is yes, and Alex has that posted in the chat. Also, I noticed Robert Bryant submitted a book recommendation in the Q&A. Robert, if you just go ahead and copy and paste that and put that in the chat so that's available for everybody to have. Okay, so next is our materials for extreme environments. This again is a kind of a modification. Originally, we had one committee on high temperature materials, and we had one on space applications. We decided to combine those since a lot of the issues were similar, but also we wanted to expand that, you know, not just high temperature, but we could also look at cryogenic types of applications so that we can really broaden the view of this committee. So Chris Smith is going to give us the overview of materials for extreme environments. Chris?
Thanks, Bob. So I'm Chris Smith at ACCI Specialty Materials. I'm a materials chemist and researcher. So our group helped put this together, Tanae Mindal, William Guzman. So thanks to them for also supplying some information. So what are the high growth areas that we've seen, you know, this year and last year? Advanced ceramics, being able to increase the fracture strength and impact resistance. Ceramics are known to be brittle as opposed to polymers. So there's been work to increase that strength. Carbon-carbon composites. So these have been around for a while, but there's lots of suppliers that are developing more advanced monomers and polymers for advancing the applications in these. So the availability, commercial scale is becoming more and more available. Multifunctional materials for hypersonics. This has particularly been a really hot topic last year and this year. So it seems last year there was quite a bit of government funding and other funding available to work on this. So it is growing. And high entropy alloys, these are metal alloys that their thermomechanical properties are tunable, and for conductivity and for corrosion resistance. We've seen a lot of that. Nanostructured materials, nanomaterial additives are being added to increase toughness and modulus, and CTE and thermal conductivity. And then additive manufacturing, we've seen a lot of that too, especially in the ceramics and the metals arena, where we've seen companies printing complete metal rocket nozzles and different types of parts. And then finally, the test method development, so that the temperatures are getting higher and the test methods are being adjusted to accommodate for that. Next slide. So some of the applications, I've got a few images here. Of course, in aerospace, they've been used for a while for thermal protective systems, and recently in hypersonics, usually ablative shielding, nozzles and thrust chambers. Jet engines, they've been used for quite a while, also jet turbines, the scramjet for the new hypersonic vehicles, nuclear propulsion systems, so hydrogen propelled nuclear reactor engines, specifically in space, require low weight, high temperature resistant materials, and even the energy sector, so thermonuclear reactors, ion battery separators for lithium ion and sodium ion batteries. This is a high temperature case where lithium batteries are exploding, you know, because the materials in there don't stand up to the charging temperature. And then solar energy concentrators have been used, and recently I've seen more with thermoelectric materials. So I split this up into two types of materials, organic and inorganic materials. So on the organic side, we have the typical thermosets and polymers. So for a long time, epoxies have been used, and they have TGs anywhere from 100 to 180 C. And more advanced epoxies have been developed, and newer thermosets have been started to see a lot of use. BMIs and benzoxazines and cyanate esters, and engineering thermoplastics like polyamides and polyamides. Those are being used to get carbon fiber and different composite temperature ranges up to maybe 300 to 400 C. But it's still not what we consider extreme environments. So you can also make carbon-carbon composites out of these. The image on the bottom, it's showing a pyrolysis method for making carbon-carbon composite. So you start with your reinforcement, whether that's carbon fiber or glass fiber or other, and then you infiltrate it with your resin or your thermoset matrix, and then burn off the organics at high temperature. So you're left with some voids, but you're left with a lot of charged carbon that stays within the part. So you can backfill that with more resin and continue this process of backfilling it and burning it off until you have a 100% mass of carbon that will maintain its weight and stability in greater than 1,000 degrees C. So next slide. On the other side, we have the inorganics. So ultra high temperature ceramics have been used for temperatures greater than 1,000 C. So there is a big desire to have refractory materials that can withstand 2,000, even 3,000 degrees C. And the caveat for a lot of these, especially for use in hypersonics, is they're operating in a extremely oxidative ablative environment. And so this can be detrimental to the part shape and the protective oxide layer. So we've seen silicon carbide composites used pretty widely for the last few decades, especially in some of the engines. The GE LEAP engine was a lot of ceramic composites. However, the ablation on supersonic vehicles, it's so high that the oxidative environment can actually use the ceramic material to catalyze oxidation reactions on the surface and essentially erode down the material leading edges. So there's been different additives developed to help combat this. I've seen a lot with diborides, tantalum silicide, yttrium oxide, or some complex carbides. We've seen a couple presentations this year on this. And essentially, the additives are helping to increase the fracture toughness and decrease the coefficient of thermal expansion and help with thermal conductivity and reflecting the heat away. So on the right side, the image is shows an example of additive manufacturing of ceramic parts. So we had a webinar a couple months back in our high temperatures committee, and they're using ceramic powder bed. So they control the laser deposition rate, and they're able to center particles into a working part. And this is really nice, although it's kind of limited in the scalability. So industrial scaling these processes has quite a bit of challenges. There's different methods for doing this type of sintering, self-propagating high temperature synthesis, and a lot of spark sintering. So there's still a lot of work to do making parts larger than 6 by 6 inches or foot by foot. This is an example of the use of the materials in a hypersonic vehicle. So this is a photo off of this company's website, and the high temperature ceramics alone will get deformed under high ablation, or such as re-entry into Earth's atmosphere. So this company worked on a type of structure to help keep the material cool by adding a coolant inside and having a porous skin that the coolant can perspirate out of to remove the heat. So it helps to reduce all the erosion and oxidation on the sharp geometry of the part. There's a specific case shown here where they used high temperature, ceramic composite covered with a zirconium borate skin, which was porous. So they did some advanced manufacturing here to make this complex structure, and this seems to be a good path forward for working on some of these vehicle skin designs. Okay, next slide. So the final part is testing. You know, historically, we haven't been doing mechanical testing in the thousands of degrees C, but now this has become necessary. So I did notice there's been some SBIR funding available just this year, 2024, for measuring tensile tester at 3,000 degrees C. And we had a couple webinars of that I'm going to show in a little bit of people doing tensile testing in 1,000 to 2,000 degrees C. So the equipment manufacturers are starting to supply high temperature fixtures that you can buy standard with their equipment. And a lot of the OEM testers, tensile testers, and mechanical testers are being heavily modified by researchers to get into this range. So a lot of the ASTM methods are having to be adjusted or updated. So there's a lot of challenges here to now form standard test methods for these types of materials. And also in aerospace reusability, there's challenges here because where one material was selected because the rocket might not have been reused or thrown in the ocean, you don't have to have the lifetime or the service life for that material. But now that they're being reused, there's a lot of questions about how to test the integrity of these in between services. So you can skip this slide. The next slide's similar. So we did have a webinar from Dr. Calvin Stewart of OSU. He was doing this high temperature tensile mechanical testing. And what he was doing is doing a lot of digital image correlation of the specimen while running the test. So they did some really fancy work also with AI and using cameras to basically drag as much data out of one test as they possibly could. So they're doing a lot of design of experiments, you know, in one run by analyzing the camera very closely and seeing how the material changes and pulls. So this is pretty interesting work that he was doing. And this is from our SAMPE journal that came out a couple of months ago. So this is with the Von Karmer Institute for Fluid Dynamics and the European Space Agency. So they're doing plasma arc wind tunnel testing. And you can see on the right side, oh, sorry. Yeah, so you can see the setup on the right side, ablative testing of high temperature material. Okay.
I think that's it. Thank you, Chris.
Thank you.
Okay, great. Thank you, Chris. Alex, do we need to do another poll question? Okay, so people can answer that. Again, if you've got questions, please enter them in the Q&A panel and we'll handle those at the end. So to round us, to finish this off, in terms of the technical committee reports, Phil Viviano from Whisk Aero will be presenting on advanced manufacturing. This is a combination, again, of two previous technical committees, one on Factory of the Future and one on rapid manufacturing. We found that there was a lot of crossover between those two committees. So we decided to combine them because really Factory of the Future is all about creating more manufacturing efficiency, which fits in with the rapid manufacturing. So Phil, turn it over to you.
Awesome. Everybody, I'm Phil Viviano. I am in production engineering at a company called Whisk Aero. We're an eVTOL company. I think advanced air mobility is another term for it, as we heard mentioned further up. So just kind of preface my presentation a little bit. You know, we've seen a lot of really good information about like specific technologies being incorporated with respect to material processing and material testing and that sort of things. My presentation is going to be a little bit more high level, a little bit more systemic. Part of the reason for that is, you know, in this committee, And in my job as a whole, I get to spend a lot of time learning a lot about a lot of different production systems. And what I've found is there's very rarely opportunities where an answer in one place is the same answer everywhere else, right? Like there's a lot of particulars in production systems. There's a lot of details that are very specific to the way one particular part might be manufactured in one particular place. And so instead, I'm going to talk a little bit about kind of the overall philosophies around advanced manufacturing and around what we believe in the committee represents the future of manufacturing and the future of production as a whole. So to start that, the general concept I want to talk to you about is something that I call next pass quality. So many of you guys are probably familiar with first pass quality, which is basically to say, you know, how good are the parts that you're building the first time? You know, how much do you have to rework? How much do you have to fix? How many issues do you pass on? I think that's well and good, especially when you're looking at active production. I think when we think about system design and how we design the factory of the future and how we design advanced rapid manufacturing, we need to think about next pass quality, which is to say that we have the part that we're building. We can understand the part that we're building. Maybe it's good, maybe it's bad. Maybe that doesn't matter. Maybe what really matters is how good is the next part that we build. So everything that we do when it comes to the future of manufacturing should always be focused on like, what's that next part? This is kind of a I don't know, hokey cliche sort of a thing, because really what it results in is a focus on continuous improvement. And how do we leverage emerging technologies to promote that continuous improvement? So in light of that, the way we see that being done within the tech committee is kind of through three separate buckets. First is upfront systems engineering. Second is the implementation of said systems engineering. And third is the sustaining of your system itself. I start with this because I think it's really important to think about like the system as a whole when it comes to manufacturing. So many of you guys have probably been on benchmarking trips, have probably seen lots of factories. One that always stands out to me, particularly extremely advanced production facility that was building a very complicated composite part. And like many of you guys on the call, I was walking through, talking with various mechanics, asking them what they liked and didn't like. The universal issue that they mentioned within that production facility was the location of parking and bathrooms, which I thought was amazing. I'm walking next to these $10 million machines building incredibly complex composite parts, and the universal issue was a simple human factors issue. And these are the things that aren't necessarily thought of when it comes to production system design. And this is where I see emerging technologies being able to improve this. So something that I was skeptical at first, but have actually seen really, really good results with, and have heard lots of good results with, are things like AR and VR being used within production. So a lot of times when a production system is being designed, like the system of the future, the issue is you don't always know what sort of unknowns you're going to uncover, right? You can design a perfect system on day one, you'll start it, and something will go completely wrong that you never saw coming. One good way that the industry has seen in uncovering these unknowns has been using AR and VR. I've seen plenty of opportunities and plenty of times when they were saying, all right, we're going to build this new widget, we're going to build this new part, we're going to build this new work cell, we're going to lay out this whole new factory. Let's give 20 headsets or 20 sessions in VR caves to mechanics, have them walk through the layout, have them basically simulate simple tasks, and it reveals lots and lots of little things like, oh my gosh, this trash can, I saw it in the chat, this trash can is like 20 feet too far. I have to walk all over here. I'm going to set down my tool, I'm going to come back, I'm going to forget where my tool was, I'm going to make this issue because this wasn't 5S properly. These little bitty things that are never thought about in the initial outlay of the production system that really, really make a difference in how well the production system performs. Time and time again, this is where we're seeing actual issues rear their ugly heads. We're seeing like the quality issues that can end up on the news are often started because of simple 5S issues or simple layout issues that just weren't thought of in this upfront process. Similar to that is, the big hot topic right now, artificial intelligence. I personally don't don't subscribe to the idea that artificial intelligence is this kind of silver bullet that can answer a lot of society's questions. What I do think is that it is a very, very useful collaborative tool. I've seen it very, very helpful in the systems engineering side up front, kind of helping what I call like systems engineering writer's block. We're not really sure what sort of requirements you need to define, what sort of requirements you need to lay out. And using this as a simple tool to basically talk through problems and to get a second perspective on problems, I've found to be very, very, very useful. And I've seen the applications of that. I think as you move into active production, designing the data systems of a production system around utilization of things like artificial intelligence is going to pay a lot of dividends. This isn't to say that you're going to have AI making decisions on the factory floor. What I do think is that it will be a part of a human in the loop supervised autonomous system that will basically help inform decisions on things like continuous improvement, data collection, data coalescing, and reporting that data out. And finally, sustaining the system. So I think the hardest part about keeping a production system advanced is creating and acting upon those feedback loops. It's all well and good to look at what you think a factory can be. The real challenge in the industrial space is existing facilities, right? Existing production lines that are running the way they run. How do we continuously improve those? And how do we incorporate feedback into that? This is an arduous task done by industrial engineers or continuous improvement engineers that consistently will take a very, very long time to identify what ends up being a rather simple fix. You think of the 5 whys, right? And a lot of this time spent out there collecting data, mining the data, analyzing it, arguing about it. Where I see the benefit of things like AI and things like big data being used in manufacturing is actually speeding up that continuous improvement process, making this data more readily available, making it automatically collected, making it automatically reported so decisions can be made faster from it. So one quote that I'd like to leave everyone that I work around with is this quote from the economist Tim Harford. And it says, "We should not try to design a better world, we should make better feedback loops." So that is to say that our goals shouldn't be to design the next incredible manufacturing system. Our goal should be to design a manufacturing system that allows the people in it to learn from each other and to learn from the system as a whole. I don't believe that there's a manufacturing system out there that looks like another one. I think they're all unique, and in that, algorithms aren't enough. So we need to use them to further our own decision-making capabilities. Anyway, thank you guys for your time, and I think we'll open up to questions and answers.
Yeah, great, thank you, Phil. Alex, do we have any more poll questions? Okay, and then, okay, so we got a handful of questions here. Most of these are directed to individual presenters. So let me start going through those. Let me start on the bonding and joining. There was a book, The Sticky Universe, that was by Kevin Kendall, that was put up there as a, and I think Felix wanted to comment on that. So Felix.
Yeah, that was exactly the book I was talking about. The distinguishing feature is he really debunks a lot of the current guidelines about you got to roughen the surface, you got to change the surface energy. He says they play an outsized role in the kind of the mythology of adhesion. He says, no, it's more entanglement, it's more roughening, does not make so much difference. And it's pretty convincing. I really recommend the book. It's really pricey, but I have it. There are also some papers I have from his where he talks about that, but that book consolidates a lot of his work from the 70s and 80s where he really goes into that. So that's what I wanted to mention, I see that Professor Greg Anderson is in the chat, and one of the failure models I brought up was from a presentation he gave, and I cited his paper. He's one of the co-authors, so I should mention that, so I'll just mention that now. So thanks.
Okay, yeah, and then there was another question for you, Felix, on the helicoil nanotube framework, the difficulties in synthesizing that.
Right, Davud, I think you're on. You want to answer that one?
You want to answer?
Yeah.
Oh, he may not be able to, Felix.
Oh, okay. I'll mention that in his work, he goes over the specifics of how he makes the fibers coil. And that coil, as I mentioned, increases that entanglement, which is such a huge factor per Professor Kendall. So the specifics are in his paper. Ping me if you want that, or Professor Ascara, he's at Wichita State. But he does have a special way to make them coil, so you can do it.
Okay, great. Thank you. And Alex, I think there's one more poll question. You can go ahead and pull that up while I keep going on the questions. Next questions are going to be sustainability. So one of the questions are you aware of any manufacturing operations that are really trying to go to a zero carbon footprint where they're using renewable energy sources to cover all of the energy needs on that?
Yes, I think to this question, there are two folds of answers. The first is that, there's a lot of new approaches being explored that directly use electricity to do the manufacturing process, especially for chemical reaction. So the electrification of the reaction is a very big area. For example, people can look into like CO2 reduction to make, long carbon chains that can be used for aviation fuel, things like through electrochemistry. So that is something that, manufacturing has been sort of integrated into, the electricity has been integrated in manufacturing process. Alternatively, people also look into, using these renewable electricity to generate heat, like I said, for plasma, resistive heating, as well as microwave. So these are other opportunities people are already looking into. So in general, there's different plugs or a component that people try to explore, but the integration of them as a company, as an organization, my understanding is still quite limited and underexplored. So there's a lot of room for that to grow.
Okay, great, thank you. And and I also just know from my interactions in the industry, yes, there are a number of companies that are looking to include more renewable sources of energy for the energy that they will use in their manufacturing operations. So it's an active area. Next question is going to be on the Extreme Environments Committee. A couple of questions, one around ASTM standards. Are they being crafted such that they're applicable for composites, or are they pretty much focused on metals and ceramics?
Yeah, I'll have to say that
A little bit of
I don't
bandwidth.
know all the high temperature ASTM. That would be something that would need modifying, but it's not exactly my area, so I wouldn't be able to answer that. Sorry.
Okay. There was another question about emissivity using the FLIR, asking if some of those issues have been resolved. Not sure if you know the answer to that.
Yeah, I'm trying to remember the article in there. They use the FLIR camera both in the European Space Agency article and also in Dr. Stewart's article. They use the FLIR camera, and he did bring up a lot of issues with that. But I have to look more into it to find the specifics on what he was talking about.
Okay. Phil, question for you. I mean, we've talked about Industry 4.0, which has been a buzzword over the last 5-6 years on it, but now starting to talk about Industry 5.0, which is really about the collaboration of humans and machines. You want to comment on kind of where you see that going? You touched on it a little bit in your presentation, but any other commentary on that?
Yeah. I'll give like kind of an anecdotal thing that I think Industry 5.0 can be really helpful for in the collaboration between humans and machines. I think that, so one time I was on this project, it was this large thing that was spooling out material. The material was consistently getting stuck in the machine, and technicians were having to reach their hand inside the machine to unstick the material, right? It was an example of like a machine that had been built without the proper human interface design accounted for, and a material system that had been never considered that particular type of interface between a human and a machine and where they would be working there. And it was presenting a huge safety issue on the factory that ended up taking a lot of like Band-Aid efforts to get it to fix. I think that when we talk about like Industry 5.0 and the future of human to machine collaboration, I think examples like that where we're like if we would have been able to collect the data about how that machine was running, about the material's performance in that machine, and get better insight to what was going on the floor through either data collection efforts or through better design for human factors. I think that would have been a huge saving grace in that particular system. So anyway, all that to say, within Industry 5.0, I think that like being able to focus more upfront about like how the machine's being used, how a human is interfacing with the machine, and being able to collect existing data and apply that to the design of the machine in more advanced ways. I think that's a big benefit of its interface.
Yeah, and I would tend to agree with that. I mean, I think sometimes people get concerned about AI and automation, that it's going to get rid of their jobs and so forth. And really, I think the value of AI and ML and automation and so forth is really to take off the jobs that can be done well by a computer and leave the human to be able to do the things that we're uniquely suited to be able to do. And working collaboratively, we can accomplish quite a bit.
Yeah.
So I'll turn it over to Raj to kind of wrap this up. And we appreciate all of the presenters and all of the participation here. Recording will be made available.
Right.
And we hope to see many of you in Long Beach. So Raj.
Long Beach. Yeah, thank you so much, Bob, and each of the leaders from the tech committees. And actually, I counted at 1.74 attendees. So we're really grateful you took your hour to be with us. You can learn more by getting involved in one of these. You're going to get a survey right after this is complete. And we will ask that, you know, there are a few questions on the survey. Which technical committee are you interested in? And Bob, we're also talking about new tech committees, you know, or subcommittees. And in hydrogen, we're very interested. So this is a great forum that SAMPE is offering, along with our chapters in global regions, that ultimately, you know, we're going to link everything together. But this is a great forum for you to engage with your peers, leadership opportunities, and grow within the MNP world. Bob, I don't have much more to say, but thank you, Alex, for handling everything behind the scenes, and obviously you, Bob, for moderating a great program. We will have the recording available in a few weeks, and that initially is made available to all the attendees by email and also on the SAMPE 365 platform.
Okay, yeah, great. And also, if there are questions that you had either asked or not asked that you want answered, join a committee and you'll have a community there that can answer those questions. So thanks to everybody.
Thank you, everyone. Thank you. See you in Long Beach.